Hello students, this is part 2 of chapter 6 and I'm going to go over a specific example of an addition reaction showing the carbocation intermediate, and then you guys are going to practice a couple on your own. So in my example, we take an alkene, very basic, and we add HBr across the double bond. So you can see the pi bond breaks. Everything else here in the starting material stays the same, but the pi bond breaks and now forms two new separate bonds, CH and CBr. That is the overall reaction that's occurring. This is a chemical equation. But there's a more in-depth view, and we call that the mechanism, showing the flow of electrons using arrows. So in the first step, what needs to happen is the alkene acts as a nucleophile. It has two electrons in its pi bond, and it's going to attack the H of this electrophile, HBr. What's going to happen is you're going to form a CH bond, but what also has to happen is this HBr bond breaks, and the two electrons here will go as a lone pair to form Br minus. So as you break this bond, you'll form an H here on this left C, and it doesn't matter, you could have done left or right carbon, but there's nothing on this C because you just broke that pi bond. So then you have what's called a carbocation, a carbon with 6 electrons and a full 1+ positive formal charge. Okay, this is your intermediate, the carbocation intermediate. In the second step, what's going to happen is you're going to then add the Br minus. So we see that here, the bromide is now the nucleophile attacking the carbon here of this electrophile, forming the CBr bond, giving the bromo-alkane product. What I want to direct your attention to is the geometry of that carbocation. This is going to be very important when we start talking about stereochemistry of these products. But basically, your carbocation has 3 groups. Here we have 2 H's and a carbon. The simplest version is just all H's. That means that has 1 extra space open to make a bond. So we have a vacant p orbital that can receive 2 electrons. And just to let you know, this is up and down. This is, this is sp2 hybridized. This carbon is sp2 hybridized because you have 3 groups attached. So it's trigonal planar. What I want to really emphasize is this is flat. So an incoming nucleophile can come from the top or the bottom. That'll play a very key role in any stereochemistry that comes out of these sort of reactions. Now you guys take a stab. What product would you expect from the reaction of cyclohexene with HCl? So pause this and write the product. If you want to take it a step further, try to write the mechanism. So the product is the chloroalkane product. What happens in a mechanism is the pi bond breaks, it forms a bond, the 2 electrons here forms a bond with the H, and I'm showing the H attaching to the top carbon here. That means the next carbon has a positive formal charge, it's a carbocation, and just to let you know, in this first step, the chloride got kicked out, and then now the chloride is the nucleophile. It'll come in and form a ClC bond, giving you the product drawn above. Okay, just to give you a feel for this, we're going to use curved arrows in polar reactions. Electrons will flow from one of these types of nucleophiles. So these are just examples. Nucleophiles can have a negative charge or be overall neutral. So you can either use something that has a lone pair, so sulfur would also work, a nitrogen with a lone pair. Carbon with a lone pair is a carbanion, it has a negative formal charge, or a pi bond in an alkene. So this can attack an electrophile shown as E. Just to let you know, triple bonds can also do this. Electrophiles can have a positive charge or be overall neutral. Some examples are acids, so it'd be the H part that you would attack. In this case, there's also HCl, HBr. An electronegative atom attached to a carbon, so you'd attack the carbon, that's partial positive, and carbonyl compounds, you'd attach the C, attack the C. Here are some examples. Let's look at methoxide. You've already seen this act as a base, this negatively charged O here with the lone pair, it'll attack and grab the H, and this HBr bond will break. So you have a new OH bond, and then the lone pair goes on to the Br, giving you the Br minus one formal charge. Here's an alkene acting as a nucleophile. You can add the H off of a hydronium ion, kick out water, so this bond breaks, the HO bond breaks to give a lone pair here. And again, when you break a pi bond, you can form a new bond, but then that other carbon will have a plus formal charge because it only has 3 groups and nothing else. And so that's the carbocation. This is the last thing I'm going to have you guys work on. Add curved arrows to the following polar reaction. So just inspect this equation. Notice what's being formed, what bonds are breaking, and use the double-headed arrow. So go ahead and pause this and try this and then unpause. So what I notice is the CO bond is now a double bond and the chloride is gone. Here, the chlorine is kicked out as a chloride anion. So what likely happened, this is negatively charged, these electrons, again, flowing from higher electron density, will go down towards the carbon to form this CO double bond. But then carbon can't have 5 bonds, so something has to give. The CCl bond breaks, and the lone pair goes on the Cl, giving you the chloride. Okay, this is where I'm going to stop, and the next time we are going to cover energy diagrams.